Hello world, this is Sean Wilkinson at the University of Alabama at Birmingham. Today I'm talking about QMachine, a web service that allows ordinary web browsers to execute distributed workflows without installing anything. So the page that you see open here is a demonstration program that is being served directly out of a Mercurial repository at googlecode.com. The reason for the really long, ugly URL is because that's the exact commit inside the version control repository. If you visit this URL, you'll be able to reproduce this experiment exactly. So now, let's run the experiment. Click the button below to launch the demonstrations. So I click, and volunteer for FastADemo here to run them. QMachine will print the results into the developer's console. A developer's console is built into all of the modern browsers. They're usually here to help us make pretty web pages, but we're going to hijack it so that we can use it as an interactive environment to do computation, much like you would use MATLAB or R, or even the shell prompt. So what we have here shows us already that when I clicked Launch Demo, it is started running code. So let's tear off this tab now to see how to volunteer for QMachine. To volunteer, so I'm shrinking it down so I can open a pair of these. I will need to go to v1.qmachine.org. V1 stands for version 1, and it is the version that we are discussing in the paper. So at the very bottom, you can volunteer for a specific box. The box is a word that really means Q, but because it was already called QMachine, I was afraid this would be confusing. It was confusing me, so I called it a box. As you can see, as soon as I clicked it, it started doing things because we had already submitted tasks up here. See, it says distributing jobs. So now I'm going to go ahead and launch another. Remember, it says volunteer for FastADemo, which is why I'm keying it in here. And then I am launching another volunteer. And as you can see, they're doing things. So let me go ahead and discuss what they're doing. And in the meantime, I guess it could be instructive to see exactly what's going on under the hood. Just as programming for a regular computer, you might be able to open an activity monitor in Mac or like a system profiler, that sort of thing. The browser can be treated just like a computer actually, and it even has its own task manager. And as you can see, the computations that are being run right now are taking about a half gig of RAM each and easily overwhelming a full core. So these are significant computations. The code itself is also part of the same Mercurial repository. I just have a convenient link here for you so that you can open the code. And when I open the code to explain it, what you see is JavaScript. Everything here is written in JavaScript. The first example, and the first three examples, in fact, actually also use CoffeeScript. This is deliberate. This is to show that you can use more than just JavaScript. You can use any language so long as it can be turned into JavaScript. CoffeeScript is being used here. So what's happening is we're submitting 2, and we're going to run a function of x that will add 2 to it. So we should see 4 appear as a result of example 1. The puts function is a print function, because in web browsers the word print actually means open the print dialog. So I created a puts function. Example 2, map is going to operate element-wise against an array. Each element will receive the same transformation, so we're going to increment 1, 2, 3, 4, 5. Each element by 2 will give us 3, 4, 5, 6, 7. Then, in example 3, and all of these are running simultaneously, by the way, which is why none of the answers have come back yet. They are chosen out of the queues, out of the boxes, randomly in order to help reduce deadlock. Example 3 will run a map pattern against 1, 2, 3, 4, 5, but then it will also run a reduce against the result of the map. The map itself this time, instead of incrementing by 2, is going to multiply by 2 just to keep things interesting, and then the reduce function is going to run against the results. We should see 2, 4, 6, 8, 10 beforehand. Then the reduce is going to result in 30. A reduce pattern, if you're not familiar with it, takes 2 elements of an array and reduces them into 1 element, and it does this repeatedly until there's only 1 element remaining. That is then the output value of the reduce function. So we expect at the end of example 3 to see the number 30 appear. Example 4, it looks more involved, but really it's nothing more than, as you see down here, example 2 in a more sophisticated manner. It's still just a map, but what the map involves is some data x, some function f to be applied element-wise, and then a box that's explicitly named and an environment that we need to prepare before we run the computation. So x, the data, is a set of 20 strings arranged as an array. These strings represent URLs that point to, because these are web pointers, URLs, they point to resources hosted by the NCBI that are Streptococcus pneumonia genomes. Each of these genomes is about 2.5 million base pairs. These will be retrieved when the function runs for each element. It will take a URL and then it will actually resolve those URLs, which is very much the same as dereferencing a pointer. It will download the file from the NCBI, and then it will execute a fractal MapReduce decomposition of the chaos game representation of the sequence alignment. I realize that's a mouthful, and I'm not going to get into the mathematics here, but we have referred to the paper, which is Almeida 2012, and we've referred to that paper within our own paper, and Jonas Almeida is also a co-author on this paper. So USM stands for Universal Sequence Maps, and the library itself is not part of JavaScript. So the environment itself needs to be aware that it needs to load this library before the computation runs, or else things are going to fail. So USM itself needs JMat, which is another library by Jonas Almeida, to load first, so that's what we do here, and then after that it's safe to load the USM library. Only after that will we actually run the computation specified by F. The computation will then take the genome that I talked about earlier, about 2.5 million base pairs, and it will look for this string inside of it that's 20 characters long. There's no biological significance to this particular string, but what I have done is I've chosen the same string that was used in Almeida 2012 in order to reproduce that experiment that was described in that report for 20 different genomes of Streptococcus pneumonia simultaneously. Of course, I'm not running 20 different machines inside of my laptop here, but I am running 2. And as you can see, they are both very busy. That's why you may be able to hear my fan on right now. You will perhaps notice also that Google Code is being used for one of these, and GitHub is being used for the other of the 2 prerequisite libraries. That's actually deliberate also to demonstrate that this workflow converges code from 2 external repositories exactly specified by their version, as well as data that is also external, and in order to execute this this entire experiment. So let's see how we're doing. Nothing has come back yet, which is a little surprising, but it's not because nothing's being done. Obviously, you see things going by on the screen. Recall that I told you these things are being done in random order, which means that the short computations that would appear first may in fact appear later, the results of them. So we'll just have to wait and see. For now, though, I'll go ahead and I'll talk about the HTTP API, how exactly these 2 windows here are communicating with the server, with QMachine itself, and how QMachine is orchestrating this workflow. So QMachine is actually orchestrating this workflow based purely on URLs, actually. If I go to see how many jobs are still waiting, there are a few, actually. But, as you can see, I was able to specify directly. And if I wanted to see how many have already finished, I could do that too. Now, to look and see exactly what's been going on, because we're impatient and we can't wait that long for them to come out and be printed, I can take one of these, which is actually a key, and you see here that this is actually a task description. The task description is written in terms of JSON, and it specifies 2 more keys, which are actually URIs. These can be resolved in a defined way to find the other resources that are needed by the computation. So if I, for instance, now I'd rather see x. Let's see x. See what the output of that computation was. Okay, this was clearly one of the sequence alignment examples. What came out of it was the position of the base, position of the probe, and the match, and the index. So something was found. We did find the 20 long string as a needle in the haystack, and we're just waiting for all 20 of them to finish so that they can come back and we can see how we're doing. For now, and you'll notice these screens keep going blank. That's partly a product of the way that web browsers work. They're not really designed or expected to run computations for more than maybe 120 milliseconds at a time. It's extremely rare ordinarily for a web page to do that as anything more than a mistake. So consequently, sometimes you'll see these go white. That's actually completely normal, so don't freak out if you see that happen. It's just a product of the way that the browsers work. JavaScript was originally designed just to update pages to script pages. It was actually designed originally to accompany Java, but Java has turned out to be a terrible technology that did not work well on the web. And finally, you see here that we have a 4. We actually did finally compute 2 plus 2. We computed a whole bunch of other things before that, but we now have 2 plus 2. So returning again to how the API works, I can specify by status and I can specify by key. Currently, as you can see, more just got finished and the queue is getting less. What's happening each time this says done is something is happening and things are being moved out of the queue into the done queue. The current implementation of QMachine that this is actually running against is using MongoDB backed persistent storage, but I could have used Apache CouchDB, Postgres, SQLite, or Redis. I'm sorry, I blanked for just a second there. So QMachine, its model itself, oh man, we're almost done. So the model itself for QMachine is very portable to different databases. And we see here was the answer to the second example, which I'll go ahead and remind you if you have forgotten that it was 1, 2, 3, 4, 5. We add 2 to each one, so we expected 3, 4, 5, 6, 7. You'll remember I said these probably don't run in order, and you're seeing that they don't run in order. It's kind of interesting that they're coming out in order. That may not happen for examples 3 and 4, but anyway, it's interesting. So you see now here that that some of these are taking 689 megabytes of RAM, 531 megabytes of RAM. It's much easier to scale this out when you have many machines rather than a very expensive single machine, and that's called horizontal scaling instead of vertical scaling. And you see here, I was right, that example 4 did finish before example 3. Recall that example 3 was supposed to tell us 1, 2, 3, 4, 5, multiply each by 2, and then add them up. That gets 30. And this is definitely, if you want to count, be my guest, this is 20 of the objects that I showed you earlier of the match objects from the universal sequence maps computation. Anyhow, that is QMachine in a nutshell. Thanks for watching, and please feel free to fire off any questions in the comments here. Thank you.